So in this question here, we have a spaceship moving at constant speed in outer space. So our spaceship is moving along like this. There's an explosion that happened that causes it to break into two pieces that move in opposite directions. So there's some speed v it's moving at. And now this object breaks into two pieces. So for that to happen, when that's going to happen, that means this one is going to increase its speed. It's going to go faster in the direction it's moving, and the second piece will be moving more slowly. Now, our intuitive answer might be that these would counteract each other and therefore would be unchanged. So there's a counteraction going on here. So let's take a look at what's going on with the momentum. Well, the system is this. This is the system, that satellite. So the total momentum of that system must remain constant. So that's just always true in the universe. So we know the total momentum must be unchanged. The question then is the kinetic energy unchanged or does it increase? Notice they didn't give us a choice of decrease in that case. So this is where our intuition about canceling out comes into play. Now the canceling out does happen when it comes to the momentum, but the question is, what happens with the kinetic energy? Well, the kinetic energy beforehand, let's say this is a 1 kilogram mass moving at 1 meters per second. That makes us have some very easy math. So the mass is 1 and the velocity is 1. So we end up with a kinetic energy of 1/2 a joule. Now afterward, let's suppose that this splits equally, that the mass is split equally, an equal split. So we've got 1/2 the mass in both cases. And so that means that this one is going to increase its speed. So let's say it increases to 1.5 meters per second. And we know that the other one must, since it's going to change its momentum by exactly the same amount in the opposite direction, the masses being equal, it's going to decrease its speed by 0.5 meters per second. So the velocity will be 0.5 meters per second. So let's now calculate those two kinetic energies for the left particle and the right particle. So let's see, we've got 1/2 the mass. Now the mass is now 1/2, and the speed it's decreased by 0.5, but it was traveling 1, so its speed is now 1/2 instead of 1, and that's squared. And so that's 1/2 to the 4th power, or 1/16 joule. Now on the other side, we have a mass of 1/2, but the velocity is now 1.5. And so that is 3/2 squared. And so we still see that we end up with 16 on the bottom, but now we have 9/16. The total energy is now 10/16. It was 0.5 a joule, or 8/16. It is now 10/16. It is increased. So we see that the kinetic energy increases. Now that is not intuitively obvious. So what we have in this case is the momentum is conserved, and the momenta are offset equal and opposite to each other. Whatever the gain in one is, the gain in the other, the loss in the other, are equal and opposite because the momentum is conserved. Now in the case of the kinetic energy, although the velocities increase by the same amount, the results are not in proportion to each other anymore. And so the fact that the right-hand side ends up with a greater velocity, a greater number squared, brings about a bigger change than the change in the smaller number squared for the left-moving velocity. But notice how we can track this out by putting in some simple numbers of like 1 to figure it out. The short of it is by applying what we know about the law of conservation of momentum, we can get to 50-50 anyway. And so that's how we do this challenging question.